Hi everyone. So this is the last video of section 2 and on regularization, and in that video we'll basically finalize our discussion of dropout by discussing interpretations of dropout, why does it work, and and the meaning of it basically, and some variants of dropout that will be introduced as part of that discussion. So one of the early introduced interpretations of dropout was presented in a 2013 paper in NIPS, in the conference NIPS. And basically the idea, it was drawing an analogy of dropout to L2 regularization because of the fact that part of how dropout works is basically the weight scaling inference rule. So basically, you can think of weight scaling inference as providing an interpretation of dropout, of what the ensemble is doing at the end of the day, is that it's as if you scale the weights going out of every unit by a certain factor or a certain weight decay coefficient, right? And this is similar basically to the interpretation of L2 regularization on the parameter updates, that you shrink the weights first, right? And even in the optimal solution, that you shrink the weights in different directions. Remember, in different directions corresponding to the eigenvectors of the Hessian by different coefficients. But here we shrink the weights corresponding to each unit, right? So instead of our basis being the eigenvectors of the Hessian of the loss, it's becoming along the features. Basically, you can think of the features as providing the basis for the weight decay coefficient for each weight parameter. So it's as if you have a different weight decay coefficient for each feature that's proportional to how much this feature will vary, right? So if there is a feature that varies a lot, then this is an important feature. Then you don't decay the weights by a lot, and so on. So actually that brings up one variant of dropout, which is called DropConnect, which explicitly builds on that analogy to L2 regularization and take it to the extreme by basically dropping every weight instead of every unit, right? So that you can even assign explicitly a different drop probability for every weight parameter, right? So that you are effectively choosing in the L2 regularization analogy a different coefficient for every weight parameter. So there is also another variant of dropout where the noise mask is not binary, right? So it's Gaussian with mean 1 and variance that's covariance matrix that's diagonal, meaning that they are independent and the variance is 1, right? So that basically these what are called non-sparse. So mu is the notation for the mask. So these are called non-sparse masks. And the idea of non-sparse masks is maybe the advantage of dropout is not really that we are dropping units, but it's that you are adding this noise to the units, right? So so that brings a discussion actually that's very interesting, and we'll come back to it later in this video, which is basically about the reason of why dropout works. Is it that the noise mask? Is it the way that the noise is working, the binary noise mask? Or is it that analogy to bagging, that we train every realization independently? So every realization is trained with its own cost, right? So there is no relationship between the cost of one realization and another realization, right? So we'll come back to this later, but first let us introduce, to maintain the flow of the discussion, let us introduce one interpretation of dropout that draws analogy into nature, actually. And that interpretation is that basically by dropping some units, you are putting pressure on the other units that are kept to learn independently of the existence or the presence of the units that are dropped. right? So you are putting pressure on every unit to learn features that are by themselves enough for prediction, right? So let's say, for example, I give you images, and the task is to recognize whether there is a face in these images, right? So maybe the network can find it enough to just detect whether there are noses, or whether there are eyes, or whether there are ears, or whether there is a mouth, right? It doesn't have to detect all of these. If it can very accurately detect the shape of the nose, then it will succeed in the task, right? But that might be very fragile, right? Because maybe some image that has a blurry nose, or taken from an angle where the blurry nose, sorry, or taken from an angle where the nose is not very clear, then it fails at recognizing. So to put pressure on the network to learn the different high-level features, Dropout can be very useful in these cases, right? Because the hidden layers are learning these abstractions. So maybe at some deeper level, the nose is recognized at some hidden layers. By dropping these hidden units in some of the realizations, you're putting pressure of learning the other features and being able to predict from the other features, and thus sharpening the recognition of these other features, right? And this has an analogy to biology, basically in sexual reproduction, where the swapping of genes between organisms creates evolutionary pressure on the genes to be good in different contexts, right? Because these genes learn to serve their task even when paired with a variety of other genes, right? When paired with a diverse combination of other genes, right? So it puts pressure on the genes as they go from one generation to the other to learn to serve their task in a diversity of situations, right? So that's one view of Dropout, okay? But then actually this view, among others, can give you an idea that maybe we don't need the regularization effect or the bagging analogy to Dropout, and it's really the binary mask because of the analogy to nature, or the analogy to the gene swapping thing, right? So remember, boosting can be, for example, is an ensemble method that doesn't that sometimes is not regularization, right? So boosting refers to changing the model as we go on, or improve the learning performance of a model using in the cost function other models as well, right? So in boosting, you don't really train the model independently, right? And that's why there is a variant that is studied in this paper right here, an empirical analysis of Dropout in piecewise linear networks that came out in 2014. And basically that paper proposed an alternative that's called Dropout boosting. And the difference in Dropout boosting is that basically you update the parameters for every realization. So I draw out a mask for every training example. Sometimes in some variants of Dropout, you draw it for every mini batch instead of a training example. But the difference in Dropout boosting is that you update the parameters with respect to the approximate loss of the whole ensemble, right? So every time I'm training a realization, I'm taking into account the loss of the whole ensemble. I'm trying to approximate the loss of the whole ensemble, right? The expectation with respect to mu, right? Whereas in normal Dropout, I train every model with respect to the loss of that model, right? So the training happens independently. But here I am tying the models together during training, right? So that has an analogy to boosting. And it is shown actually in that paper that Dropout boosting does not deliver the generalization effect, which is the improving the generalization error of as Dropout, right? So it's really the analogy to bagging or training the models independently, and not just the binary mask. And another evidence is that Dropout can have a regularizing effect even when using non-sparse masks that delivers the generalization effect, right? So remember, there are these two really different roles or different functionalities that Dropout is doing. One is the sparse mask, and that has the analogy to the gene swapping and the analogy to nature, right? By putting pressure on every unit to learn. And one is the regularization effect, which is basically how training is done, similar to bagging, is that you train every realization with respect to its own cost function and not tying the models together. Thank you.